Hello and welcome to another lecture on trusses. Today we'll be discussing classification and static determinacy of trusses. So let's begin. Let's start with the classification of trusses. Generally, they can be divided into simple trusses and compound trusses. Simple trusses have a regular arrangement of bars consisting of triangular truss cells. Compound trusses are formed out of several simple trusses and are used to cover large spans. Let's discuss compound trusses in more detail. A compound truss can be formed out of two simple trusses by connecting them with a common joint and a bar, as shown here on the right. Another way of forming a compound truss is to connect it with three bars. A compound truss can be formed out of two simple trusses by connecting them with a common joint. In this case, a more complex arrangement of supports is required, otherwise the truss will be unstable. As you can see in the example given here, both supports are simple and the total number of reaction forces is 4. A compound truss can also be formed out of several simple trusses by connecting them with several bars and joints. Here you can see an example of a compound truss connected with 4 bars, 2 common joints, and an extra joint connecting the bars. Another class of trusses is complex trusses. Here you can see an example of such a truss. This truss cannot be divided into simple trusses as it doesn't contain any individual cells. Note that the bars are not connected at the intersections without joints. Let's consider an example of the transformation of a simple truss into a compound or complex truss. Here you can see a simple truss consisting of 3 triangular truss cells. The addition of 2 bars and 2 joints transforms this truss into a compound one, where the 2 simple trusses are connected with a bar and a common joint. On the other hand, the addition of 2 bars and a joint can transform the simple truss into a complex one, which does not contain any triangular truss cells. Now we will learn how to determine whether we can solve a truss with one of the methods we've learned so far, namely the method of joints and the method of sections. We can write 2 independent equilibrium equations for each joint in a planar truss. Therefore, the total number of equilibrium equations equals twice the number of joints, J. If you remember, we started the solution of trusses in the method of joints with finding reaction forces from 3 equations describing equilibrium of a whole truss. As a result, the considered system has 3 extra equations which are dependent. These 3 equations are used for checking up the solution in the method of joints. The number of unknowns in a truss consists of the number of reaction forces R and the number of truss members M, which is equal to the number of unknown internal forces. When the number of knowns equals the number of equilibrium equations, we can solve the truss using, for example, the method of joints. The condition for solvability of trusses is called static determinacy. When the number of reaction forces and truss members equals twice the number of joints, the truss is considered statically determined or solvable. This means that we can solve it using either the method of joints or the method of sections. When the number of reaction forces and truss members is larger than twice the number of joints, the truss is considered statically indeterminate or not solvable using the methods we discussed. This means that the truss has too many unknowns and can only be solved using advanced methods, which you will learn in more advanced structural engineering modules. When the number of reaction forces and truss members is smaller than twice the number of joints, the truss is considered unstable. This means the truss has too few unknowns or constraints preventing its movement, and it will collapse. Let's evaluate the determinacy of several structures. To do that, we need to calculate the number of reactions, the number of truss members, and the number of joints. The first truss has 3 reaction forces comprising of the horizontal and vertical reaction forces in the left support and a vertical reaction force in the right support. The truss has 5 members and 4 joints. The sum of reactions and truss members is 8, which is equal to twice the number of joints. And therefore, this truss is determinate and can be solved. Let's now consider the second truss. This truss has 4 reaction forces, 2 reaction forces per simple joint. Additionally, it has 16 members and 10 joints. The sum of the reactions and truss members is 20, which is equal twice the number of joints. Therefore, the truss is determinate and can be used using the methods we have learnt. Let's consider the determinacy of 2 other trusses. As you can see, these trusses have a similar arrangement of bars. The only difference is in the right support, which is a simple support in the top truss and a roller support in the bottom truss. The first support has 4 reaction forces, 2 reaction forces per each simple support. The truss also has 8 members and 6 joints. The sum of reactions and truss members is 12, which is equal to twice the number of joints. Therefore, the truss is determinate and can be solved. The second truss has 3 reaction forces, 8 members, and 6 joints. The sum of reactions and truss members is 11, which is smaller than twice the number of joints. Therefore, this truss is unstable and will collapse. Let's consider another 2 trusses. As you can see, these trusses are similar, except that in the top truss we have an extra bar in the middle, while the bottom truss has a different left support. The first truss has 3 reaction forces, 14 members, and 8 joints. The sum of reactions and truss members is 17, which is larger than twice the number of joints. Therefore, this truss is indeterminate and cannot be solved using the methods we've learned so far. Since the truss has 3 reaction forces, its indeterminacy comes from having too many bars. As you can see, the middle cells are not triangular. They are more complex. This type of indeterminacy is called internal. The second truss has 4 reaction forces, 13 members, and 8 joints. The sum of reactions and truss members is still 17, which is larger than twice the number of joints. Therefore, this truss is also indeterminate. Since the truss is made of triangular cells and has 4 reaction forces, its indeterminacy comes from having too many reactions. This type of indeterminacy is called external. As we've just seen, when the sum of reactions and truss members is smaller than twice the number of joints, the truss is unstable because it does not have enough members or reactions to constrain it from moving. However, an entire truss or part of it can also be unstable even when the sum of reactions and truss members is equal or larger than twice the number of joints. In this case, instability can only be determined by an inspection of the truss. As in the case of indeterminacy, instability can be internal or external. A truss is externally unstable when all of its reactions are concurrent or parallel. Internal instability results in the truss becoming a collapsible mechanism. Let's consider the following trusses. The first truss has 3 reaction forces, 8 members, and 6 joints. The sum of reactions and truss members is 11, which is smaller than twice the number of joints. Therefore, this truss is unstable and will collapse. This truss contains an unstable middle cell, comprised of 4 bars and 4 joints. The second truss has 3 reaction forces, 9 members, and 6 joints. The sum of reactions and truss members is 12, which equals twice the number of joints. However, this truss is still unstable and will collapse. In this case, the instability is also internal and could only be identified by inspection of the arrangement of truss members. This truss contains 2 unstable middle cells comprised of 4 bars and 4 joints. Let's consider now 2 cases of external instability of trusses. This type of instability is introduced by a wrong arrangement of supports. The first case of external instability occurs when all the reaction forces in a truss are concurrent. In the example shown here, the truss has these 3 reaction forces. As you can see, the lines of action of these reaction forces intersect at the right support, making these 3 forces concurrent. This means that these reactions cannot prevent the truss from rotating around the right support. The second case of external instability occurs when all reaction forces in a truss are parallel. In the example shown here, the truss has these 3 vertical reaction forces. As you can see, the lines of actions of these reactions are parallel, which means that they cannot prevent horizontal movement of this truss. The internal stability of a truss depends on the arrangement of truss members and can be determined either by inspection or by structural analysis. If the truss is internally stable, a unique solution for internal forces in the truss can be found. An unstable truss will have several solutions. A simple truss is always internally stable, while the stability of a compound truss depends on how the secondary simple trusses are connected. The stability of a complex truss is difficult to determine by inspection. Usually, complex trusses are analysed to determine their stability. Let's consider 2 trusses. The first truss has 4 reaction forces, which are not concurrent. It is formed out of triangular cells. Therefore, this truss is stable externally and internally. The second truss is similar to the first one. The only difference is that it has an unstable middle cell consisting of 4 bars and 4 nodes. As a result, this truss is externally stable, but unstable internally. The truss shown on this slide has 4 reaction forces, which are not concurrent. Therefore, this truss is stable externally. The inspection of the bar arrangement shows that this is a compound truss made of 2 simple trusses connected by only 1 bar. This type of connection is not sufficient for stability of the right simple truss. Therefore, this truss is internally unstable. Thanks for joining me for this discussion into the stability and determinacy of trusses. Check out our other videos, putting this theory into practice and solving trusses. Bye for now.